Let's think about it for a second. From the blood moving through your veins to galaxies spinning across the cosmos, pretty much everything in the universe is in motion. But how does it all work? Well, it turns out the same basic rules that steer a planet in its orbit can also tell you exactly where a thrown ball is going to land. And in this explainer, we're going to break those rules down.
So it really all kicks off with a simple question, one that every kid has probably wondered. If I throw this ball, can I actually figure out exactly where it's going to land? And the answer is a big, resounding yes. How we get to that yes reveals some of the most elegant and powerful ideas in all of physics. But to predict that beautiful arc, we have to start with something way simpler.
I mean, let's be real. Motion in the real world is messy. It rarely happens in a perfect straight line. Things curve, they speed up, they slow down. So how on earth do you make sense of all that complexity? Well, the secret, as we're about to see, is to take that complicated curve and smash it into its simplest possible parts. And that is our game plan. Before we can even think about tackling that soaring arc, we've got to get a handle on motion in just a boring old straight line. Physicists have a fancy name for it, rectilinear motion, but it's the bedrock for everything else we're going to talk about. So let's build that foundation. To really describe any kind of motion, there are two concepts that are absolutely critical: velocity and acceleration. Okay, first up, velocity. Now, in everyday chat, we tend to use speed and velocity like they're the same thing. But in physics, that difference is a huge deal. Speed is just a number, how fast you're going. Velocity, though, adds direction to that number. So it's not just 100 kilometers an hour, it's 100 kilometers an hour north. And that little bit of direction, it changes everything. And next, you've got its partner, acceleration. This is all about how your velocity changes. So if your velocity is changing in any way, you're speeding up, you're slowing down, or even just turning a corner, yep, you are accelerating. This was a massive insight from Galileo. While he was studying things falling, he realized that the key wasn't how fast they were going, but how that speed changed over time. That's the core idea of acceleration. All right, so we've got the basics for a straight line down. We've got velocity and acceleration. But remember that ball from the beginning? It's not moving in a straight line. Its path is a curve. So our simple one-dimensional tools just aren't going to cut it. We need a way to handle direction that's more sophisticated than just forward and back. And that new tool is the vector. This is the key that unlocks motion in 2 or even 3 dimensions. Vectors are how we bring that crucial element of direction into our math in a really powerful way. So here's the big difference, laid out plain and simple. A scalar is just a number. It has a size, a magnitude, and that's it. Think about the temperature or the speed your car's speedometer shows. A vector, on the other hand, has both that size and a direction. It's not just 100 kilometers per hour, it's 100 kilometers per hour north. Things like velocity, acceleration, and force, they're all vectors. And getting that difference is what lets us level up. You know, the really cool thing about vectors is that we can actually work with them just by drawing. If you want to add 2 vectors together, you just use the head-to-tail method. You draw the first one, then you start the second one from the tip, or the head of the first one. The grand total, what we call the resultant vector, is just the arrow you draw from the very beginning of the first one to the very end of the last one. It's a simple little trick, but it's incredibly powerful. But here is where vectors become a real superpower. It's not just about adding them together. The real magic is that we can take any single vector that's pointing off in some weird diagonal direction and break it apart into 2 simpler pieces that are perpendicular. A horizontal part, we'll call it the x component, and a vertical y component. This little trick, splitting one complex motion into 2 simple ones, is the absolute key to solving our problem. Okay, we've got our tools, we understand motion on a line, and we have vectors to handle all the different directions. Now it's time to put it all together. We're going back to that thrown ball, and we're finally going to figure out that curved path. And this brings us right to the huge aha moment, which Galileo figured out centuries ago. That complicated arc of a thrown ball, it's not actually one complicated motion at all. It's really 2 simple motions happening at the exact same time. And here's how it breaks down. Horizontally, along the x-axis, if we ignore air resistance, there's nothing pushing or pulling it. So its horizontal speed just stays the same. It just cruises along. But vertically, along the y-axis, it's a totally different story. The ball is in free fall. Gravity is constantly pulling it down with a constant acceleration. So its vertical velocity is changing every single second.
And that's the secret sauce. That's how we do it. We can treat these two motions as completely independent problems. We use one set of simple equations for the easy, constant speed horizontal part and another set of equations for the constant acceleration vertical part. You solve them separately, and when you put the two results together, boom, they perfectly describe that parabolic path of the projectile. We've cracked it.
And these principles go way beyond just throwing stuff. Take uniform circular motion, something moving in a circle at a steady speed. Even though its speed isn't changing, its velocity is, because its direction is constantly changing. And if the velocity is changing, that means it's accelerating. And for circular motion, that acceleration vector is always pointing right towards the center of the circle, constantly yanking it into that curved path. So look, this is way more than just some abstract problem for a physics class. These principles of motion, velocity, and acceleration, they are totally fundamental to how our world actually works and how we build things to work within it. Think about stopping a car. The physics here is non-negotiable. It tells us that your stopping distance is proportional to the square of your speed. So what does that actually mean for you? It means if you double your speed, say you go from 30 to 60 miles per hour, it doesn't take you twice as long to stop. It takes you 4 times the distance. That's not just a suggestion, it's a hard rule of the universe. And these applications are absolutely everywhere. This is the physics that determines safe speed limits. It's used to measure a driver's reaction time, the delay before they even slam on the brakes. Your phone's GPS. It is constantly crunching numbers on your changing position vector to know where you are. Every single time you see a sports commentator predict the arc of a home run or a free kick, they are using the physics of projectile motion. Even airline pilots have to plot their course by adding their plane's velocity vector to the wind's velocity vector to get where they're going. So what's the big idea here? What's the main takeaway? It's actually a pretty profound concept that even the most complicated-looking motion, whether it's a planet orbiting the sun or a simple ball flying through the air, can be understood. You can make it predictable just by breaking it down into simpler, independent pieces that all follow a clear set of rules. And all this leaves us with one last, kind of mind-bending thought to chew on. From the cells inside us to the galaxy we live in, everything is constantly moving, which makes you wonder, if nothing is ever truly, completely stationary, what does it even mean to be at rest? Maybe that simple idea, just like motion itself, really just depends on your point of view.